Thank you, Felipe, for the introduction. Let me make it clear, I will speak English, but any question in Portuguese and Spanish will be very welcome, right? Okay, we will try to cover some introductory material at the beginning, and I know that for the faces that I can recognize sitting there, that it will be hard to say something new at the beginning. Maybe in a few classes I will be able to say things. Also, it will be interesting that you don't keep any question to yourself. If you have any question along the lecture, I mean, you want to ask me after the lecture, or you want to make an appointment and we discuss that between lectures, right? That would be quite nice to do. Then, because some of you know everything, and some of you I don't know what you know, right? Then, okay, then let's start with the Fourier transform with very basic thing, and let's see if we have time, we will reach something that is not so basic. Okay? Okay, let's start with then if we have a function that is in L1, then it makes perfectly sense to define the Fourier transform in this way. When this is the inner product between these two vectors. Okay, certainly, if you are in L1, this integral makes sense in the Lebesgue sense. And second, you can say, why do you define, sometimes you define the Fourier transform differently. You don't use the 2 pi here. You remove the 2 pi, but then you pay a price. You have to put a constant somewhere. Then if you want to avoid to put a constant in the front, you put the 2 pi there and so forth. Then let's see some properties. As a map, you take functions that are in L1 into functions that are in L infinity, right? You take absolute value here. This is bounded if you put absolute value inside. This quantity have absolute value 1, then you have that. And it's the equality holds if f is positive, because then you have f of 0 is equal to this. Okay, you are mapping the Fourier transform is a linear map from this space into that space, but in general, you are not here. You are in a better space. You have that, in fact, f is continuous. If you write who is f of x plus h, c plus h, minus f of c, and you apply one of the Lebesgue theorem, you will get that. You apply Lebesgue dominated convergence theorem. In fact, it's still a little bit better. It's not only that you are continuous, you decay at infinity. How do you prove that you are in this space? That then in general, if we put all together, means that you are sending L1 into the continuous that vanishes at infinity. That is a subspace of. Okay, how do we prove this part? Well, let's do it in one dimension. The idea of the proof. In one dimension, you take the characteristic of the interval AB. Is this clear, the characteristic? Okay, you take this function that is 1 in the interval AB and 0 outside, and you take the Fourier transform of this, you are going to have the integral and then you can compute this explicitly. Then you have then you see that this quantity have absolute value 1, the 2 and the 4. Then these behave, you decay like that. Then if the characteristic functions of intervals decay, then the linear combination of this also will decay, and then by density you will have the property that you want. If you want to do it in Rn, you do it that by block. I mean, you do it by rectangles, and the simple functions are dense. Then you can approximate a function that is the characteristic of any nice set by squares and so forth. Okay? One small thing to notice here is the following. Let's recall something from the beginning. If, for example, you have this interval is 1, 1, then this quantity here is exactly sine of 2 pi c over pi c, I think, right? This is 1, this is minus 1, and so forth. You have this. Okay. Then notice that one thing, that even if you start with a real function, this is a real function, in general, the Fourier transform will not be real. If you want to preserve that real functions take Fourier transform to real, then you have to take this function to be even. It's the only way that you have. Second is, notice to begin with that this function have a very fast decay. I mean, it's 0 outside this interval. Then you have a nice decay, very nice decay, but it's not smooth. It's not C1 in particular. However, this function have completely the opposite. This function doesn't have a nice decay. This function is not in L1. But this function is the restriction of this one that is an entire function. This function is an entire function it's analytic in the whole complex plane. Then you can see from the beginning that we will emphasize that the Fourier transform switch decay with smoothness. Okay, let's see other properties. What is, if you translate a function, means that you move it to the right, then what is the relation with the Fourier transform? If you take the translation and take Fourier transform, this is equivalent to multiply the Fourier transform by this number, I believe. Yes. And the other way around, if you take the Fourier transform of this quantity, you have, this is f of c, translation of minus h, f. That means that if you take translation and take Fourier transform, it's exactly the opposite if you take Fourier transform and then multiply by the exponential. That's the way that they They don't commute. Okay, let's see one more property. Let's suppose that we have dilation, and we take this function here and contract or expand the graph dependent if A is bigger than 1, or let's make it positive to simplify our life. Okay. Then what is the Fourier transform of this? Is why this makes sense? Well, if you do this transformation, this dilation, you are not changing the L infinity nor. Right? This doesn't change the L infinity nor. This transformation that you divided by A and multiplied by 1 over A to the n doesn't change the L1 nor. Okay? Then it makes sense. Let's have this. Okay. Any question at this point? No? Okay. One of the nicest things about the Fourier transform is the following property. If you have f and g are two functions in L1, you can define this convolution This is again a function in L1. Right? And you have this property that the convolution of by applying Fubini, you get this. Then convolution is a complicated operation because you need to translate and compute the integral and so forth. Then you have this property that if you take this complicated operation and take the Fourier transform, this becomes just a product. Right? And this is quite nice if you go here and you see that if you take L1 is a vector space, but if you add the convolution, you can say that this is an algebra. Because you take two functions in L1, you take convolution, you're still in L1. It's an algebra that doesn't have a unit element. Then this is also an algebra, and this of 8, okay, all the operation here go into the operation here when you are linear, but the convolution go into product. Because you are an algebra in L1 with respect to the convolution, you are an algebra in L infinity with respect to the pointwise product. In the same way that you have this, you have that if you have two functions in L1, now you have to kind of weird notation because you use the x for the original function and the c for the one. You can pass the hat to the other part. By applying Fubini and so forth, you apply the hat like this. Okay. But of course, I mean, most of the time you don't want to pass the hat. What you want is to have the inner product. Then what you have is this. If you define f inner product with g to be f g dx, then you have this. F hat g is exactly equal to f g hat evaluated in minus. Okay, I will write this. Okay, let's see some examples. Let's see some examples in it. Okay. We already saw this one. Let's do example 2. Suppose that we have this. Let's do it in one dimension first. You have this, the exponential of the absolute value multiplied by 2 pi with a minus to make it. Then this function is not C1. Right? It's almost C1, but it's not. Then if you take the Fourier transform, you will have this. Well, it's not too hard to do it because you write the Fourier transform of this, you split the absolute value in 2 pieces, and you integrate each piece separated, and you do it. Right? I mean, it's not, it's a small computation to do this. Then you write this in 2 pieces, and you can integrate each piece separated. Now you can find the primitive of this one, you integrate, and the other one, and you will get this. Okay, let's see the business between decay and smoothness. Okay, this function has a very strong decay exponential, but it's not so nice smoothness-wise because it's just failed to be C1. This function is okay. It doesn't decay too fast, right? But this function is the analytic extension of this one. This, when you restrict to the real line, this function becomes this one. And this function is analytic, but just in this strip. Because you have a singularity here in I, maybe a minus I. Then you are analytic in this strip. Analytic. Then if you decay exponential, we will see, you will have something to do with, you can say something about the analyticity of this one. Okay. This one decay faster than exponential. I mean, this 0 outside this interval, then it's much better. This is an entire function. Okay, this doesn't go there. Okay, we will. Okay, if you are in more dimensions, this formula is still true, but require more computation. In the example 2, in n larger or equal to 1, you have this. Some constant that depends on the dimension, 1 over 1. Gee, this is C here. I'm sorry, this is C. Okay? You have to correct me. I will start to do more and more mistakes. Okay? This is C squared to the power n plus 1 over 2. Okay, this constant depends on the dimension. Has to do with the gamma functions. Okay, this is the computation. All these things are in any book in Fourier analysis, in particular in the note with Felipe Linares. Right? A small advertisement. Okay, there is a formula for complex integration that complex integration tells you that the cosine of ax, x squared plus b squared dx for a and b positive is equal to pi over b exponential of minus ab. Maybe gonna, okay? This is one of the, when you do contour integration in complex variable, this is one of the first few that you learn. Then, if you take the Fourier transform of this quantity in one dimension, since this function is even and the exponential is split into sine and cosine, the sine part disappears, then you get only the cosine part. And the cosine is even, then it doesn't care too much which sign you put there. Okay? And then you are going to apply this formula, and A has to be positive to apply that formula. Then the sine of this one doesn't count because the cosine is even. Then when you do all this computation, you finish exactly with this. Okay? Then you can see that it's kind of nice. If you start with this function, you take the Fourier transform, you go here, and then you take the Fourier transform of this one, you go here. Okay, this is, in general, this is not true because you have two problems. This is true because this function is in L1, and when you take Fourier transform, you are in L1 again. And this function is even, and this function is even, and there is no problem with the sign. In general, you don't have this possibility. You take this function that is in L1, you take Fourier transform, you are here, and this function is not in L1. Right? Then you cannot go back and apply the Fourier transform as you would like to. Okay, then what do you do in that case? Well, let's wait for a moment. Let's add one more property that we are missing. Then we'll stop in property 7. Let's go property 8 now, before we return to that. Property 8. Suppose that f is in L1 and xk of f is also in L1. That means that not only you are in L1, that when you multiply to the component k of your variable that is x, you are still in L1. This is growing. That means that this function has strong decay in that direction. Then if that is the case, you have that the derivatives, then this function has derivatives in the direction. And what you have is that derivative with respect to k of this is 2 pi I ck f. And now we have to check the sign because this is. Okay, what is that saying? That you have a better decay in the direction, let's say, k. That means that your function has some regularity in that direction. You switch regularity with decay, and you have that. Then it's very simple. What you do, you're going to take the Fourier transform of this, And you say, well, but this is exactly the derivatives of this. Okay. I'm going to say, oh, this is exactly. Then if I take the derivative with respect to c sub k of this, I need to divide it by minus 2 pi I, what else? Like this? But I want to put, okay. Now it's okay? Okay, now this one cancel this one, right? Okay. Therefore, if you don't want to have this 2 pi I here, you start with the 2 pi I inside here. You have the 2 pi I here. Okay? Then, if you want to make it look nice, you put 2 pi I here, 2 pi I here, and then you don't have to put that. You put a minus there, put a minus there. Then you have like this. And then, of course, this you are integrating in x. You are taking derivatives in this other variable. You assume that this is true. And this is what you have here. Okay? Okay. Okay, let's try to study the opposite of this one. That this one say, if you have better decay in some direction, then you have some regularity in the size of the Fourier transform. Let's do the opposite. Well, we need a definition. Suppose that we have f in L1. You can put p here, right? But let's do it with L1, and then we will put the p there and all that. You say that g is the k partial derivatives of f in the L1 sense if the limit when h tends to 0, h being a number, of f of x plus h e sub k, you compute the increment of your function with respect to the k coordinates, you subtract this g, and this tends to 0. You're saying that this increment converges to this function g in the L1 sense. Then you are not taking pointwise derivatives. I mean, for example, if you take derivatives of this function, let me give you an example. If you take if this is your f, the derivatives of f in the L1 sense will be, here will be 1, here will be minus 1, and here will be 0. Then if you are continuous, you can do it almost pointwise, this part. And now you can say, can I take another derivative? Well, no, you don't have the right, you have a jump. Okay, you cannot keep going. Okay, then if you have a derivatives in the L1 sense, you can call g of x the partial with respect to the k variable of f in L1. You can put this in LP. You can put p here, and then you have to put p here and p here. Okay? Then the property says, suppose that f is in L1, and the derivative with respect to x sub k of f is in L1 too. Then you're saying that you have regularity in that direction. That means that you have, the Fourier transform have a stronger decay of that. That implies, what do you expect? Suppose, what will be the Fourier transform of this? Then if you integrate by part, you pass the derivatives to the other side. And since you are integrating by part, this will be 2 pi I c sub k and this is exactly 2 pi I c sub k Fourier transform of f of this. Then if that is the case, then you can say that in particular, see, why this function have a better decay in the component k? This is an L1 function. This is in L infinity. You are saying that all this function, when you multiply by this quantity that is growing, it's a polynomial of order 1, is still in L infinity. Then you have some decay in that direction. Okay, now, before we go to the formula, like we would like to return, we take the Fourier transform of a function that is not necessarily in L1, and we want to go back to the original function. But we have the problem that may not be in L1. Any question up to here? Okay, let's compute. Let's go back and make one more computation, and we will not erase this one because we will need it for the next. We need this computation example. We want to compute the Fourier transform of this quantity. Okay, this is the Gaussian distribution. In n equal to 1, you have something like this. Okay? Depending on who is A, you have that. Well, that function has both properties that you want. It has a very fast decay exponential, and have all the derivatives that you wish. Okay? Okay. Then let's go to the property that if we have this function, who is this one? Right? Therefore, what is the Fourier transform of this one? The Fourier transform of this one will be the Fourier transform of the original one, square root of A, right? And I'm using this formula that I erased. The formula of the dilation that say the following. Recall, the formula of the dilation was this. If you have the dilation of A of x is f of ax, then right? Okay, then it's enough to compute the Fourier transform of this one. We compute the Fourier transform of this one. By this trick, we know the Fourier transform of this one. Okay, then let's compute the Fourier transform of this one. And since everything is exponential, it's nice. Then the Fourier transform of this is these are exponential. Then we can write this. This is the product of j equal to 1 to n. And we can do the integral in each piece separated. Right? Because you can write this, the exponential of the sun is the product of the exponential. You can apply Fubini and get into that. Now we are going to complete the square of this. What do we have? The exponent that we have there is minus pi multiplied by 2i x sub j c sub j plus x sub j squared. And this is equal to minus x. This is the square of the first, the double product of the first with the second, if the second is I c sub j. But then we are adding the square of this. We have to subtract the square of this. Then we have to subtract this. And what is this is minus here, because when you take the square of this, you have a minus, but you have another minus here. This gives you plus. In order to have the identity, you need this. Therefore, this integral is this integral. Okay. Okay, this is, then let's do this carefully because we are going to use this many, many times. And in fact, maybe something new that we will say at the end of the class for many of you will have to do with this Fourier transform. Then what is this integral? Okay, then suppose that you are integrating here. This is x, this is c. You put j there. You're integrating really here. This is the level j here. Then you can use that this function, if this is the real part and this is the imaginary part, this is an analytic function, right? Then the integral of this will be 0. This integral is going to disappear when you move that because you have very strong decay, right? I mean, if this is r, you take the r squared. This is fixed. This is the part that controls the business. This is going to that. Then the integral in the top and the integral on the bottom will be the same at infinity. Therefore, this integral is equal to this integral. Okay? And now, what is that integral? Then you take this. Then you change variable and you have this. And now you remember that the integral of this quantity, I think, is the square root of pi, using the trick with polar coordinates and so forth. Therefore, this integral is 1. Then all this integral is 1. You have the product of this quantity, and that gives you this. Therefore, you have proof that the Fourier transform of this quantity is in self. But if you go here, you have proved that the Fourier transform of this quantity is 1 over a to the power n half e to the minus pi, and then you have to is this okay? We have this. Okay, we need to be sure that we remember this because we are going to use it several times. At least in okay. Then we don't need no question in this computation. In particular, if we take A, let's to be sure that I'm not jumping. If we take A to be 4 pi t, what do we have? We have that the exponential of minus 4 pi squared t x squared of c is equal to 1 over 4 pi t n half exponential of minus a c squared 40. Okay. Why do we care about this? Okay. I claim that this is a very nice kernel. Okay, which one is that? Maybe I have this written in the opposite direction. This is who is this kernel here? It's called the Gauss. Okay, the Gauss kernel, but you're going to allow me to write this in this way. I should write this X and C here. Okay, I don't want to write, let me change that this like this. It's not very elegant, but it's what it. Okay, I want to see how this change with T. Okay. This is equal to 1 over T to the n half K X square root of T, where K of X is 1 over 4 pi n half exponential of minus c squared over 4. If I multiply by this, I get this. If I evaluate in this quantity, I get this one. Is that correct? We can check okay, this is now I can if what let me define this with let's use the variable x now because we're going to get confused. If I have this function is positive. The integral of this function is 1. How can we get into that? Well, you can do the computation, if you wish, or you can go back and see what is the value of this function at 0. Okay? But in any case, this function have area 1. If you don't believe, do the transformation and do the integral you just did. Then what is exactly that you are doing with this kernel? Okay. Okay, I apologize, I'm using this. Then you have a function that this function have an area 1, and you are when t goes to 0, you are making this 1 over t goes to infinity, you are making everything to contract at 0. That means that if this is a graph of k of t, at least in one dimension, when t goes to 0, you are contracting all this. K of t will concentrate all the mass at 0. Then this is an approximation of the unit. Therefore, you have the following. F of x is equal to the limit when t goes to 0 of the convolution with this kernel. And I have to explain in what sense this limit holds, but let me write this. Okay, this is true. This is a convolution of the unit. I mean, this is an approximation of the unit. The unit will be the delta that is not in L1, but this is in the L1 sense. Is that clear? When you take this quantity is approximate all the mass at the origin, you can prove. If you don't follow this argument, please ask me, and we will do it together in my office. Then this will go all the mass at the origin. That will be the delta that you recover this one and the limit in the one side. Then you have this quantity that is explicitly this one. And this is exactly equal to the limit when t goes to 0 of the translation in x of this function. Okay. But now, recall that if you take the Fourier transform of this, okay, I have to write this carefully 1 second. I need to be sure this is going to be the transform. Okay, where is the y? Is it the translation? X of this function. This 40. Then what I'm saying is that this function that you have here is just the Fourier transform of this one. Okay, let's see that this is true. First, to put the translation here, you can remove the translation here by putting, you can commute this part with this one. And the Fourier transform of this one is that one. That's what we have here. Then if we to put translation here, if we translate here and we put it inside, it's exactly to put the exponential. Okay? Then if we use this, that is a property of the translation, and this identity that we have here, we have that this is a hat. Therefore, this is the limit when t goes to 0 of this quantity, exponential of 2 pi I xc exponential of minus 4 pi squared t squared, Fourier transform of this as a function of x, f of, then I have to be careful because this is going to be a function of x. I have to put here a function of x dx. Okay, I have to put y. Now I'm going to use a trick that you can pass the hat to the other side. I'm using the trick now that this is equal to this one. See, this function is in L1. This has very strong decay. This is the original function that was in L1. We change the hat to this side. And now, what is this? Well, if this were not there, means that you take the Fourier transform. You take the Fourier transform inverse means that you evaluate in not in minus, in plus, and you recover that. You cannot do that because, in general, this function is not in L1. You need something that helps you. And this is the guy who helped you because this decays very fast. Okay? Then this is true. In the L1 sense, you have proved this. This f is equal to the limit when t tends to 0 of this quantity. That means that you can go forward and backward if you accept that you're going to have to leave that the limit is in the L1 sense. You take your function in L1. This function will be in L infinity. This function is in L1. It decays extremely fast. Then this all makes sense. And this limit makes sense because it's equal to this one. And it will be equal to this. Then this is called a summation. You are putting something that helps you to add. Okay, if you don't put that kernel there, it's that. Okay. Notice few things. Any question? Okay, let's notice a few things. Notice. What happens if f is in L1 if and his Fourier transform is also in L1? Suppose that this is the case. It's not a general true, but suppose that. Then what do you have? You can put absolute value here. This is a function in L1. The limit, when t goes to 0, this is 0. You have an L1 function by Levex. You can pass this. You have that this limit will be equal to this limit. In that case, you have, in the L1 sense, in that case, we can pass the limit inside because the limit of the integral is the integral of the limit. Then you have, in L1 sense, f of x is equal to exponential of 2 pi I xc f c dc. Okay? But moreover, if you have this and this, what can you say? If f is in L1, his Fourier transform is a continuous function. This function will be a continuous function, it's not in L1. And now, this function that you are taking the Fourier transform of this one will be a continuous function. because this one is in L1, you are computing the Fourier transform without the minus. That means that you're evaluated in a minus, if you wish, right? Then if you repeat this, this will be the Fourier transform of the Fourier transform of this evaluated in minus x. But this is in L1. Therefore, all this is continuous. Then you have said that this will hold is continuous. Then this is continuous, and this will hold pointwise. In particular, if f is in L1 of R, and f is continuous at x sub 0, you have that this is true. Pointwise, this is a property of being a nice kernel, nothing else. If you have continuity in one point and you are in L1, this number, sequence of number, converges to this value. In particular, you have converges every point here. Okay. Okay, any question before we go to the L2? No question? I doubt that I have said anything new to most of you or many of you. I don't know, but okay. Let's do the L2, and then we can at least finish. Okay. Let me write this formula here because we will need it. In particular, if A is equal to 4 pi t, we have exponential of minus 4 pi squared t. Okay, L2, let's do the Fourier transform in L2, and the Fourier transform in L2. Okay, L2 is better because L2 has some geometry. You have to define the inner product between two functions that are in L2, and L2 is a Hilbert space, and you have many things that is. L2 is reflexive, and you have infinitely many better things in L2 than in L1. The problem is that I cannot write this, except by cheating. But, if you have a general function in L2, this doesn't make sense. Okay? This cannot be written. Then you have to start with, suppose that f is in L1 intersection L2. Then you can write that. Okay? What we want to prove is, our claim is, if f is intersection here, then we have the Fourier transform. Then you have first, this function is in L2. And second, the L2 is preserved. The Fourier transform preserves that. This is the claim that we want to prove. Okay, let's review that. If you start with a function that is both in L1 and L2, the only thing that we know at this point is if you take Fourier transform, this will be in L infinity. We don't know more than that. Well, we are going to prove that you are in L2. Moreover, you preserve the L2. If this is the case, then you will be able to define by density this space. You have the Fourier transform defined here, but it's an isometry. Right? Then you can extend that to the whole space. And in fact, you're going to prove that it's not an isometry, it's a unitary operator. Then if you prove this, you're in extremely good shape because this is dense. You can extend the definition of the Fourier transform from here to here in a unique way. Okay? And you're going to prove not only that you are an isometry, that you are an unitary operator. Okay, and that's a small trick, but we will jump this part. Okay, then what is the trick to prove that? Let's go slow because there is an order in all this. Of course, I erased what I needed, then we will have to recall that, but let's. Okay, what do we know? Let's go to the proof. Okay, so suppose that we define G of X to be F of minus X conjugate. Why do you do that? Because in a moment you will see that it's the right thing to do. But of course, if you take the conjugate of a function, you don't change the L2 nor. You don't change the L1 nor because everything is absolute value. If you reflect the variable, you don't change that. This function is also in L1 intersection L2. You're not changing any size of anything because everything is absolute value. Okay. Then compute the convolution of this. Where is this? Convolution of these two functions. To begin with, this is in L1 and this is in L1. Since this is in L1 and this is in L1, this belongs to L1. But also you have the property that convolution in proof functions, you have this problem this proposition that if you don't believe it or you want to know the proof, we can do it together in my office. It says the following. Suppose that you have F belongs to LP in Rn. Suppose G belongs to LQ in Rn. Suppose 1 over P plus 1 over Q is equal to 1. Suppose that none of them is infinity or 1. Then F convolution with G is a continuous function that vanishes at infinity. Continuous vanishes at infinity. Why? Okay. Why? Because you're going to use holder. Write this. Right? Write the convolution. This is the convolution of F with G in X. This is the convolution of F with G in F plus H. Then the difference of these two is equal to this integral then take absolute value here, apply holder. If you apply holder, this function is in LP, this function is in LQ, then this is the what? This is the translation. The LP nor of this, you are computing the LP in Y, but the X doesn't affect you, the H affects you. Then this is less than the translation in H of F minus F in LP with G in LQ. You use holder. X for you is a parameter. You put it here, you see that the only thing is H. Now, why this is going to be small? Well, you prove that the translation is a continuous operator in LP. Why? Because is this true if you have compact support continuous? Is true, and compact support continuous functions are dense in P, and now you are using that P is not infinity and Q is not infinity. Then you have that this is a continuous function. Therefore, in particular, since you have that this function is in L2, G is in L2, and F is in L2, the convolution of two functions that are in L2, in particular, is continuous and vanishes at infinity. Okay? Therefore, for the previous one, we have an F convolution G of X, pointwise, is equal to the limit when t goes to 0 of this. This is what we just saw. If you have a function that is in L1 that happens to be continuous, then the pointwise limit holds when you do this trick. What happened at x equal to 0? At x equal to 0, you have that f convolution g at 0 is equal to the limit when t tends to 0 of then you put x equal to 0, you have only this. And now let's see, why did you choose your G that way? Okay, who is F convolution with G Fourier transform? Well, we saw this is F convolution with G. I mean, product with this. Okay, who is this? By definition, this is minus 2 pi I xc G of x dx. Who is this one? Well, we define to be that one. Then this is exponential of minus 2 pi I xc f and minus x here dx. Then you change minus x by x. This is going to give you this. Is this okay? And this is equal to this. That is equal to this. Therefore, this quantity that you have here is just this. Therefore, what you have here is the limit t goes to 0, exponential of minus 4 pi squared t c squared okay. Then this limit exists because we know that from this top. Okay? What does Fatou lemma say? Let's recall Fatou. Fatou say if you have a sequence of positive functions, then the limit inf is comparable with the limit inf and which one is larger than the other? Well, it goes like this, right? Why? Because you put the function that are 0 and 1, so forth. Right? Fatou say this. See, I mean, the way to remember for me Fatou is you choose the even to be this one and the odd to be that one. Therefore, we have the limit inf is equal to the limit if the limit exists. Therefore, this is larger than this. Why? Because this is more than the limit inside. When you put the limit inside here, when t goes to 0, there is no t here. When t goes to 0, this goes to 1. You have that. Then you have proof that this function, right, is in L2. Okay. Then we have proved this part. Okay. But now, if you have proved that this function is in L1, I mean, all this function is in L1, this is an identity. This is an equality. Right? Because the limit of the integral is the integral of the limit. If you can bound all this, but now you know that all this function is in L1. It's equivalent to say this. Then the limit exists and is equal to that. And now, who is this? This is, by definition, is f of x minus y, g of y dy evaluated in 0. Right? Then is this one. This is dy g of x minus y, f of y. It doesn't matter how I write the convolution, and x is 0. Right? Therefore, what is this? This is f of y who is g of minus y? G of minus y will be exactly this. Then you have this is exactly the L2 norm of a square. Then you start with that and you finish with this one. Then you have proved that for functions that are in L1 intersection L2, that you can use that definition, that you have the property with the convolutions, you have the identity like this. Therefore, there is a unique way to extend the Fourier transform from this space that is dense in the L2. Then we have this situation. Any question? Question? Okay, now we have this situation. The Fourier transform go from L1 into L infinity. Well, in fact, you go into the continuous that vanishes at infinity. That is a subset of this space. And in fact, you can get this. You have an equality hold if f is positive. And you have the Fourier transform can be extended from this space into L2, and you have that is an unitary operator. That means it's not only that you preserve. Go to it. You go like this. And in fact, it's onto. You can prove that it's onto by doing the trick of passing the hat to the other side. Okay, then you see that this is an operator from here to here that is onto. Isometry. You can prove that as an operator from this space to this space, you are not onto. But still you hold that the constant that you can put here is 1. The constant that you have here is 1. Okay. Okay. We will see in the next class or maybe later that is there anything that is between L1 and L2 go between anything that is between L infinity and L2. Okay? And since this node is 1 and this node is 1, you will see that the node that you will have in that case is at most 1. That is the theorem will give you, but it's not 1. It's better than 1. Okay? Okay, let's go to one more space that we can define the Fourier transform. And then we will go to some of the statements that we said, and we will try to do it. Okay, Fourier transform in the Schwartz class. Okay, what is the Schwartz class? Schwartz class are functions with a complex values, such that f for all alpha and beta in you get any multi-index. Suppose that you have alpha is equal to alpha 1, alpha n, and beta also is a multi-index. Then these derivatives exist. What do you mean derivatives? X beta means derivative with respect to the first component, beta 1 times, the second component, beta 2 times, the n component, beta n times. And what do you mean for x to the power alpha? Means x1 to the power alpha 1, x2 to the power alpha 2, xn to the power alpha n. Then you take this function, you compute any number of derivatives in any direction that you wish, and you multiply by this polynomial in this component. This is in L infinity. These are the functions whose derivatives decay as against any polynomial. Okay? These are the Schwartz functions. And let's define this as a vector space. You can put some semi-node. We don't need that. This is what you are saying here. Okay? It doesn't. What you're saying is, I take all the derivatives and I decay very fast. How fast doesn't matter what polynomial you give me here. I still, when I multiply there, I still, this function belongs there. You can put here L1. Why? Because you can put, since this is true for all this, you can put this like this. This is in L infinity, then you can pass to the other side, and this is integrable. Or you put to the power n if you wish, or 2n or something. You have, if with a lot of power here, you are in L infinity, you have to be integrable. You just divide it. Okay. Okay, can you give me an example of a function here? For example, if a function has compact support and it's infinity, you are there. Because to take derivatives doesn't matter. What you do, you still have a nice function that has compact support. Since you have compact support, this part, even if it's very big, you don't see it because you are 0 afterward. Another example is this one. Because when you take this function and you compute derivatives, you multiply by a polynomial. And the polynomial doesn't, the decay of this is stronger than any polynomial that you have. Okay? Then, what is the point in all this? The point in all this is what happened with the Fourier transform with this. See, multiplications, when you take Fourier transform, multiplication by powers go into differentiation, and differentiation go multiplication by powers. Then if you forget the 2 pi I sine, this is going to be, this is, I'm forgetting the two, this is C, okay, I'm forgetting the 2 pi. Remember that if you put this decay inside, it goes into differentiation, and this one, this go into this. Therefore, you can pass the derivatives. You're going to have the Leibniz rule here. When the derivative hit here, you have something that has power. When the derivative hit here, you have something of the same style. It's differentiation and multiplication by powers. Then if you start with a function that is in the Schwarz class, and you take Fourier transform, you finish with functions that are in the Schwarz class. You are doing the same business. Okay? Why do you want to complicate life? Well, because if you are in the Schwarz, if you have any function that goes into here, the Fourier transform goes into here. See, you preserve the L2 because this is a subset of L2, this is a subset of L2, this is 1 to 1. And you can prove that it's onto. Because you preserve the L2, you can, in the moment that you do this, you have the only guy that you can send to 0 is 0. If this is 0, it's because this is 0. Then if this is the case, you can define the Fourier transform from the dual of this into the dual of this. And the dual of the Schwarz class are temporal distribution. Okay, there's a huge class, huge. Okay, that we don't want to explain, specify. Okay. Okay. Let's see some theorems that say the following. Okay? We are going to say now uncertainty principles. Well, what do you mean uncertainty principle is any principle that says the following, that the Fourier, the function and the Fourier transform cannot decay both of them as fast as you wish. Okay? Let's go and do one, let's go back. Before we go there, before this, let's go and do a theorem that is an intermediate step. Theorem. Suppose F is C infinity with compact support. Suppose the support of F is contained in the ball of center 0 and radius r. This means that f of x is equal to 0 if x is larger than r. Okay? What can you say about the Fourier transform of this function? Okay, let's go back and see. Well, certainly if you have compact support, you are in L1, you are in L2, you are in the Schwarz class. If you are in the Schwarz class, the Fourier transform sends you into the Schwarz class. But you should be better because, I mean, you are compact support. Then let's see, what is the Fourier transform? The Fourier transform is this. Right? Then, in particular, suppose that I decide to extend this analytically. Suppose that this, I write this as a complex variable. Suppose if you can do it each component exactly the same, then you write this way. What do you get here is that this is exponential of minus 2 pi I xc e to the minus, plus 2 pi x eta f of x dx. Okay? See that this factor here now is this. Before, if this is real and this is real, this has absolute value 1. Now I am assuming that I want to extend this definition into complex variable. I am putting the imaginary part here, and putting the imaginary part here gives me an exponential. This grow, or this decrease, depend if x depend of this, but I mean, if you are integrating the whole domain, it's eta is here in some direction, it grows. But it's not a big deal. Why is not a big deal? Because x, this function have compact support. This integral is only in this ball. Therefore, the x here is only for x that are inside this ball. Therefore, this, what is the value of this function? How big can be this? Well, if I put absolute value here, I put absolute value inside, this part I still have absolute value 1. How big can be this? Well, eta is part of our business. The x, the larger that you can be with the x is r. Then this is less than exponential of 2 pi r eta, some constant that depends on f. Okay? But now look what. Is this function analytic? Call this C. Call this C. X, suppose for the moment that x is fixed, exponential of C is analytic. Exponential of C multiplied by a constant is analytic. And this is a sum because it's an integral. Therefore, this is all analytic. If you don't believe, you take the derivatives, you apply Cauchy. I mean, this is as you can do it in many ways. You can see that this is the limit of analytic function, or you can take, I mean, the derivatives of this with respect to this component and see that this is 0 because you can pass the differentiation inside and you finish this. Then you have that this function is analytic. Where? Everywhere. Then f extend is an entire function in each component. Entire in each variable. C sub j, that is C sub j plus I eta j. Entire means analytic in the whole domain. Okay. In fact, I can take derivative here. In fact, you have this estimate. Okay. Let me remove this. Suppose that you multiply here you take C plus I eta to the power, remember this is a multi-index, alpha, f of phi plus I eta. What is this? This is a correspond to take the derivatives, well, I have to put 2 pi I maybe here. This corresponds to take derivative with respect to x here. Right? If I take derivatives, I get into that. Maybe I have a minus here. Maybe this is I. Okay, now I can integrate by part and pass that here. Then this is minus 1 to the absolute value of alpha. Absolute value of alpha is the sum of alpha 1 and alpha 2. And you have this. And you have the derivative with respect to alpha here. And now you use the same trick. You say, I put absolute value here, I put absolute value here. There is a piece here that grows is when this complex number multiply this complex number, but you are still with compact support. You only care what happens when x is less than r. Then you have this property. You have that f for every n, you have an f of c plus I eta is less or equal to some constant that depends on n and f, 1 plus c plus I eta to the power n exponential of minus 2 plus 2 pi r eta. Why? Because this number here, you are going to pass this in absolute value to the other side that is bounded. And you can do that for any quantity that you wish. You can choose this one to be even, and you have it. Then the only thing that grows is when you start to put complex number here. Right? If you put this one to be 0, you are not saying much. You are saying that you decay fast, and this is true because you are in the Schwarz class. What you are saying is that you grow, you are a function that is entire, and you decay when you are purely real, and you start to grow when you start to get into the complex numbers that have imaginary part. This is the theorem that says if f belongs here, if f belongs here, and the support of f is in this ball, then for all this you have this. The nice part of this theorem is that it's if and only if. If you have an entire function that satisfies this, it's coming to be the Fourier transform of a function that has this source. Let's do it that. Converse. If f, let me say that in one dimension is simple, is entire on C to C and satisfy this property and satisfy this boundedness, and for all n, you have this is a constant then f is the Fourier transform of a function where f is infinity with compact support in the ball of center support of this. Then this is a very interesting theorem because it tells you, it characterizes completely what can you say if the function have compact support and it's infinity. Then the Fourier transform is an entire function that satisfies this growth and the other way around. Okay. This will be important later on because we don't know an extension of that if you remove analyticity. What will be the equivalent? We will see what you mean by removing analyticity in a moment. Any question? Okay. Okay, let's go to uncertainty principle. And let's start with the simplest one. Uncertainty principle is say very roughly that f and the Fourier transform cannot be to concentrate. Around the origin. Or if you wish, they cannot decay too fast, both of them. Okay, let me give you the first one. Example. Heisenberg. Okay, it's a big name for this very simple question. Suppose that you have a function in the Schwarz class. And you write this. X sub j, d sub j. If you repeat the two index, you have summation symbol that you don't write. And you write f hat dx. Okay? You have all the right to integrate by part here because this function is in the Schur class. They decay extremely fast. The derivatives decay extremely fast. This is just something that grows power 1. Then if you do that, you can pass this to the other side, and you're going to have that this is exactly equal to n f hat, that this is n dl2 nor square, right? I integrate by part. This is, you have the sum here in give you n. If you develop this, this is give you minus x sub j dj of f hat dx minus x sub j dxj of f hat f. And this is less. This is dxjf in L2, xjf in L2, doesn't matter if you put conjugate or not. And this is exactly the same business. You put this with this, and this here, then you have a 2 here. Then you have proof that the L2 nor square is less than n over 2 the Fourier transform of x sub j of f in L2 dx sub j of f in L2. And now, since this function is in the Schur class, his derivatives are in the Schur class, in particular are in L2, therefore this is equal to n square n sub j f. What is the Fourier transform of the derivatives? Is c sub j f L2, but now we have a 2 pi, right? Somewhere. Then we have a 2 pi somewhere here. Okay, then 2 pi. We are using that the Fourier transform of this is plus or minus. If you do the computation, you will find the sign. Okay. Then that tells you that for some constant pi over n, maybe you have x sub j f c sub j f this. Then you cannot say, if somebody gives you a function in L2, this number and this number cannot be as small as you please. You cannot be too concentrated at 0. That means that when this is very close to 0, you don't see this. And this is very close to 0, you don't see this, because you have the lower bound that is the L2 nor. Okay, that have some physical interpretation that is outside the business. But you cannot tell me that the function f multiplied by this function is very close to 0, and this is very close to 0. You cannot have that. If this were as close to 0, you can make this as small as you please. Because in the moment that f is close to 0, this is very small. In the moment that the hat is very close to 0, supported very close to 0, this is very small. You cannot make these two quantities as small as you please. Okay, this is the first identity principle that we have. Let's make another one. And they have to do with Hardy, and all this that is from a comment that Wiener made, that the Wiener comment was this, that the f and the Fourier transform, both of them cannot decay as fast as you wish, doesn't matter how smoothness. Remember that the Fourier transform switches smoothness with decay. Suppose that you have all the smoothness that you wish. Still, you cannot have that the Fourier transform and the function can decay as fast as you wish. Then Hardy proved the following. Suppose that f of x in one dimension, that was his proof. If f of x is capital O of exponential of minus a pi x squared, and f is capital O of exponential of minus b pi c squared. A and b are positive quantity. If a times b is more than 1, f is 0. If a times b is equal to 1, f is some function that have f of x in absolute value is exactly exponential of minus pi x squared. Okay, what do you mean is this? Look, this here. Look here. How fast this decay? Well, I can choose the a here whenever I want. And his Fourier transform decay like 1 over a. You don't have anything better than that. Is this decay like this? Is this decay like this, and you multiply these two and you get something more than 1, you are 0. You cannot have that these two guys, with this pi here, give you more than 1. And when you are you can compute that explicitly. The capital A here is a, little a, and the b is 1 over a. You cannot have anything better than that. Okay? You will see that this is a very crucial for the Schrodinger equation that we will be studying. That is the goal. Okay. Then this, people extend this to higher dimension and to LP. Let me. Okay, now I have to give the reference if I find it. Okay. I think Tangabello was the one that proved this. And Tangabello. Okay. But in the LP setting, it was Colin and Price proved the following. Okay, they proved this. If they are not dual, by the way. And one is finite. At least one. In one, between 1 and infinity. One of them is finite. If a times b is more or equal to 1, f is 0. You lose the equality here. I'm not asking this to be in L infinity now. I'm asking to be in LP and LQ, and one of them, at least one, P or Q, let's put it, P or Q less than infinity. You have that. Okay. Then it's not that you have to be bounded, you have to be integrable. That's the reason why you lose the equality. And you have the same problem. This is the best that you can do. And P and Q are not dual, okay? Okay, let's see that there is another one that is very nice and much simple to remember. And maybe we will prove this next class, depend of your interest. This is a paper by Horvander, but really it's a result of Berlin. He proved it in one dimension. He says, suppose that f is in L1. If f of x multiplied by f, this multiplied by exponential of 2 pi x, see, and in one dimension, then this is a product, normal product, you can put it like this. dx dc is finite, f is 0. Okay, let's say that if you are close to 2, if you are very close to 2, I mean, this is Horvander, okay? Or Berlin. Whenever you, this is Horvander wrote the paper, right, that he found after Berlin died. They talk about this proof. He never published, and then Horvander published that. Okay, notice something. Notice this. If x multiplied by phi by 2 is less than x squared plus y squared, right? Oh, c squared. Is that okay? Then if I plug this here, this implies if this is finite, okay, let me even do it in a nicer way. You have that 2x multiplied by c is less or equal to a x c suppose that both are positive, no problem. This is a x squared plus then we have that. Plug that here. Then if you have these quantities finite, and this quantity is finite, if these two quantities finite, this is finite. And if this is finite, this is 0. And now go here to this setting and put P equal to Q equal to 2. And this is exactly what you have. You recover this result because you have it here with 1 over A, you have 0. Is this okay? You are saying if this is finite, this is in L1, and this is in L1, and this is B, and this is A, and the product of this is 1, then you have to be 0. Then you see that this is a very simple way to recover that. So you have class here at 4? At 3? They have class here? Okay. Okay, okay, Horvander the proof of Horvander can go up to here in n dimension, but then you have to put this. Okay? Okay, but let's go even more picky to that. You have that x multiplied by phi is less than x to the power p plus phi to the power q, right? This is by Young inequality. Then Horvander tells you that if f of x 2 pi x to the p dx plus fc c to the q 2 pi dc is finite, then you are 0. Okay. Then Hormander is very sharp when you are with P and Q equal to 2, but you will see that it's not sharp when you start to go with P and Q, one of the two far from 2. For example, if one is a compact support, you will not recognize this. Okay, let's do something. We will start with this condition next time. Okay? You will start with this condition next time, and we will say what happened. Let me put that something in your mind. Say the following. Suppose that F is infinity with compact support. Let's do it one dimension. Then this function cannot be in L1. Okay, we will start with this next time. And if we will try to give the proof of Perlin-Hormander result next time. Okay, this has to do with the maximum principle and so forth. Okay, thank you.